Hi everyone, thanks for joining us today. My name is Darren Harris, Senior ESD and Air Tightness Consultant for Suho. The topic of discussion for this webinar is Introducing Air Tightness. Before we begin the presentation, just a little bit about Suho. At Suho, we are passionate about driving Australia's transition to a sustainable built environment. Suho sees air tightness as not only an important cornerstone for this transition, but also a practice that can increase the commercial value of the built environment. This presentation will take approximately 25 minutes. At the end of the presentation, questions will be made available via a survey. It will be sent to an email address you signed up with. This information can be reviewed as necessary to complete the survey questions in order to obtain one AIA Development CPD point. On completion, we'll send you a certificate of attendance. Questions about the presentation can be submitted to Suho. Please email info@suho.com.au. Other air tightness inquiries can be submitted to air@suho.com.au. Before we commence the presentation, let's run through what we'll cover. Firstly, we'll look at some air tightness testing basics, including how we test for air tightness and how we express the results. Secondly, we'll discuss the benefits of being airtight and talk about whether or not an airtight home can in fact be bushfire resilient. Thirdly, we'll discuss how to plan for an airtight built environment and how we might apply testing to larger commercial buildings. And finally, we take a look at requirements for airtightness under the Australian Building Code and the Green Star standards. The basic concepts of airtightness include blower door testing and air leakage measurement. Let's look at those briefly. Firstly, what is blower door testing? Essentially, it's an airtightness testing system incorporating a fan to pressurize the built envelope, coupled with a gauge for measuring the level of airtightness achieved, and a way of facilitating simple diagnostic techniques for finding leakages. So what is air leakage? Air leakage is the uncontrolled movement of air through unintentional cracks and gaps in the built envelope. Leakage points occur at building surface penetrations, within the building components, and in the building envelope, particularly at structural elements, material joints, and even sometimes a combination of these things. Okay, I hear you thinking, wait a minute, isn't air important in a building for breathing? Yes, absolutely it is. However, we need to ensure indoor air quality is suitable for continued human health. Air tightness helps us take control of the air that we get to breathe day in and day out. In a vehicle, we rely on operating windows or running ventilation systems to manage our air supply. Why not our home, where we spend most of our time? As Dr. Hartwig Kunz, head of the Department of Hygrothermics and inventor of Woofy, says, ventilation is important, but it must be on purpose. Relying on uncontrolled infiltration of air through our leaky built envelopes from the outdoor environment is not a healthy practice. As Dr. Kunz stated at a presentation to Prefab Oz, to realize healthy and durable buildings, an integrated envelope and HVAC design approach is essential. So, how does an air tightness test work? Here are the basic steps. Step 1. A test door is installed, featuring an industrial fan. The size of the building and how leaky the building is determines the number of fans required. Capable of moving 8,000 cubic meters an hour at pressure, a fan is more than capable of testing large homes. Each test door can facilitate a further 2 fans, suitable for smaller commercial buildings. Multiple test doors can be run simultaneously for larger commercial buildings. Step 2. Running the fans creates a pressure difference between outside and inside, causing air to flow through the leaks in the building's envelope. The success of a blower door test relies on fans to create the pressure difference necessary to take a reading. For example, a 14-story high-rise building designed and constructed with a prescribed air barrier with a permeability level of 5 may only need 15 fans to create the pressure difference to achieve a test result. The same building, designed and built with no target permeability, and no prescribed air barrier will likely be very leaky and require upwards of 30 fans, with no guarantee that a pressure difference necessary for a permeability result will be achieved. Step 3. Pressure is created as air moves past the fan. A calibrated gauge displays this information as a flow rate. This gauge is called a manometer. It uses a differential building pressure, the pressure at the fan, and the details of the calibrated fan that the system is driving to calculate the leakage flow rate. Step 4. The building pressure is varied during the test, and the resultant flow rates averaged for an accurate reading at 50 pascals. A compliant test must meet the requirements of the Australian Standard or ATMA technical standards. While a test can be recorded manually, software such as Airtight for a single fan test or TechLog for a multiple fan test can be used to monitor and record the results. Data recording displayed by the two software tools during a test is shown here. In Australia, the air tightness test results should be expressed in terms of air permeability rate measured at 50 pascals of pressure. Air permeability is defined as volume or cubic meters of air per hour leaking through each square meter of the building's envelope surface area at 50 pascals of pressure difference. As per the diagram, the building's surface area, put simply, is the sum of all the external walls, floors and ceilings or roof areas. The concept of air leakage rate can be difficult to grasp. Here's a visual representation of what it looks like in a building envelope that might help you. The orange squares X, Y and Z provide a visual representation of 1 square meter of a building's surface area. The white rectangles visually demonstrate the size of an opening in a building envelope. That would result in 3 different levels of air permeability as shown. On the left, a permeability score of 20 at 50 pascals as per box X is the current Green Star maximum for commercial buildings. In the middle, a permeability score of 10 at 50 pascals as per box Y is the ATMA proposed residential requirement for 2025 code. And on the right, a permeability score of 5 at 50 pascals as per box Z is a measurement considered by many to be airtight. A discussion of air tightness results may include air change rate or air changes per hour, expressed as ACH at 50 pascals. But what is it? ACH is defined as the number of times per hour air leaking through a building's envelope will replace or exchange the volume of air within the building at 50 pascals of differential pressure. Although not technically correct, air change rate at 50 pascals is often used to describe air leakage rate in Australian dwellings. This is because 1. It's simpler to understand than air permeability for most people. 2. Based on a well-known rule of thumb, it can be converted to a real-life air change rate by dividing ACH by 20. And 3. It can easily be compared to the 2015 CSIRO Air Tightness study of Australian dwellings, built mostly between 2010 and 2014. As per the graph above, 129 dwellings were tested and the results documented in the CSIRO House Energy Efficiency Inspection Report. Some of the findings were: the average Australian dwelling has an ACH of 15.4 at 50 pascals. 1/3 of the buildings could be considered well sealed with an ACH of 10 at 50 pascals. Very few homes came close to the passive house standard of 0.6 air changes at 50 pascals. The NATO's assumption of 10 to 12 ACH at 50 pascals is in fact generous, with the average home therefore not actually achieving its calculated star rating, and that building quality and attention to construction detail were in fact the most significant factors in the building envelope's performance. Importantly, while ACH may be reasonably interchangeable with air permeability in dwellings, it's not suitable for the results of large architectural or commercial building applications, where the volume is relatively much higher than the building's surface area. Let's look at the diagnostics involved in finding air leakage. The use of a blower door will supercharge a visual inspection, making the invisible both tangible, because the air leakage pathway can be felt, and quantifiable, as the impact of a leakage can be measured on the building's performance. To find air leakage points, an experienced air tightness tester will run the test at around 30 to 35 pascals of pressure. Set consistently, this pressure allows a comparison of the air leakage points using some relatively simple diagnostic tools. A typical inspection involves the following equipment. Hands. Great for building air barriers, but also really good at detecting air movement and sensing the force of air. Smoke pens. Providing a stream of smoke, they are great for seeing air movement and pinpointing the location of an air leak. They are particularly useful in videos for conveying the extent of leakage issues. Similar to smoke pens, fog machines. Best used over large areas to see where air is escaping through the envelope. Thermography. In a conditioned and occupied building, this method of fault finding can be exceptional at showcasing air leakage. Although during a construction, a low temperature differential between inside and outside may make it a less used option. And finally, eyes. Fluttering insulation or tape or wraps are all telltale signs of air leakage. Recording these leakage details can help drive continuous improvement by designers and builders by 1. Defining repetitive air leakage faults, 2. Tracking the effectiveness of fixes, and 3. Identifying building components and product installation issues. What are the benefits of having an airtight building? Perhaps the most well-known benefit to building airtight is the reduced heating and cooling loads on the building. The difference between the air conditioning loads of a standard Australian dwelling and an airtight dwelling is thought to be around 20 to 25%. The difference between a passive house designed dwelling and a leaky dwelling with 25 to 30 plus air change rate could be as much as 50%. Also, an airtight building will be less responsive to external changes in climate, meaning peak load energy demands are reduced. Other benefits include comfort. With lower and reduced incidence of uncontrolled air leakage, there's less potential pressure differences in a space. This means less drafts and random temperature differences between surfaces. Acoustics. Reduced gaps in the building envelope reduces the transfer of sound from outside. Indoor air quality is also markedly improved. Less openings has the effect of keeping unwanted pests and critters where they belong, outside. An airtight envelope can prevent up to 70% of PM 2.5 particles, a pollutant responsible for respiratory irritation, illness and disease, entering through the building envelope. This can be as much as 90% when combined with HRV or ERV systems. With less particles in the air and lower variation in temperatures, mechanical ventilation systems can perform at their maximum efficiency, recovering heat energy and providing fresh filtered air. Interstitial condensation is also reduced. The prevention or reduction of airflow means less humid air can be moved through the constructions, meaning the potential for moisture infiltration into the structure and the potential for mold is reduced. Also, wind washing of insulation layers is reduced. This leads to better envelope performance and longevity. The impact of lower infiltration can also be seen in the release of accurate sustainability, where a lower infiltration rate can, under the non-rating mode, be used to improve a building's star rating. It's clear an airtight dwelling can provide many benefits. Can it help us with climate change resilience, in particular bushfires? Managed well, but not on its own, an airtight building can be an important first step in managing the extreme pollution caused by smoke ash and dust from a bushfire. As can be seen from the satellite photos of New South Wales and Queensland during the 2019 bushfires, smoke can drastically impact vast areas, often hundreds of kilometres away from the flame zone. Successful air pollution resilience in a bushfire relies on three principles. Firstly, air tightness. An airtight dwelling can stay smoke resistant for longer. However, eventually saturation occurs. For an example, a dwelling with a permeability of 3 will provide the best part of 6 hours protection before inside pollution reaches outdoor levels. An Australian standard dwelling with a permeability of 15 will provide less than an hour. Secondly, air infiltration units or purifier systems can assist to maintain healthy air quality levels. The HEPA filters in these devices are exceptionally good at removing particles of wildfire smoke and dust, reducing concentration levels by around 85%. Domestic portable units can service 40 to 50 square meters of floor area using just 10 to 30 watts of energy per hour. What about air conditioners? Air conditioners are not able to operate with HEPA filters. Air conditioners with ionizing air purification features can help, but most have photocatalytic filters that are not effective at filtering smoke. Mechanical HRV or ERV systems also should not be relied upon unless non-standard high-quality electrostatic filters for smoke have been fitted. The final principle is measurement. Invest in air quality monitors for the detection of PM2.5 and PM10 particles if possible for both inside and outside the dwelling. This will allow you to compare the relative air quality, allowing you to determine if opening doors and windows is really an option and when. Don't rely on human sensors. They are not good enough to detect the PM2.5 particles. The smoke smell we can sense comes from the larger PM10 particles. In summary, many factors other than smoke will need to be managed in the event of a bushfire. Passive house designed and high performance air tightness homes tend to be built better, have fewer gaps, crevices and openings, meaning that they can be less vulnerable to ignition, particularly from embers reaching the home's interior. However, like all homes in a bushfire hazard zone, it's vital to have a well-considered and implemented fire resilience and evacuation strategy. We can test for air tightness and find leaks in buildings, but how can the industry create airtight buildings in the first place? The difference between an airtight building and one that is not is the deliberate design and inclusion of an air barrier. The red pen test is a planning activity. It can be used effectively for all built environments from dwellings, as per the floor plan on the left, to multi-story commercial buildings. It's called a red pen test because typically for clarity, a red line is drawn around the building's envelope. The aim of this activity is to identify components, assemblies and materials that will form the air barrier. Notably, the red pen line generally follows the insulation layer, and in doing so defines the unconditioned area outside the barrier which will be excluded from the air tightness test zone. Areas like car parking, plants and storerooms. This air barrier is ideally refined and agreed between the designer or architect and the building contractor constructing the building. In a successful red pen test, the line must be continuous in both plan and section detail. This requirement for continuity drives and influences the decisions to be made about the air barrier construction long before ground has been broken. Over time, this method has proven to be the cheapest, easiest and most practical means of communicating the air barrier to the entire project team, including on-site trades and contractors. Having designed and constructed the building, how do we test for air tightness and interpret the results? What about large commercial buildings? With residential buildings, more often than not, a whole building test is easily achieved. However, commercial buildings require multiple blower-door systems for a successful test result. Several testing methods have been developed as the industry attempts to balance testing complexity and equipment levels, and as building contractors attempt to wrestle with the costs and the logistics of such a test. A whole of building test should be the ultimate goal, particularly when aiming for maximum green star points because 1. It's the only practical way to obtain a true air permeability reading for the building, with all external surface areas subject to the test. 2. It is accurate, as internal air leakage through risers, ducts, vents, stairwells and lift shafts, etc. are generally taken out of the equation. And 3. If the building has been constructed and designed for airtightness, less fans, setup and time may be needed than for an advanced or guarded testing method. Compartment testing is often considered as an alternative. While certainly requiring less equipment, it is easier, faster and less expensive. However, this type of test is only really suitable for certain building types and room testing, namely apartment buildings, isolation rooms, comms rooms, etc. The issue with this test is that air leakage between floors and ceilings through mechanical systems or other adjacent parts of the building grossly distorts the actual leakage via the external envelope of the building. Also, the envelope area actually tested is not likely to reflect the other parts of the building's construction. Permeability measurements from this test should not be offered as valid test results. It should only be considered for obtaining qualitative information on leakage failure points. An advanced or guarded test can seemingly be a more attractive proposition. Using pressure in adjacent floors or compartments to prevent internal air leakage to other parts of the building, this approach tests all types of constructions in the air barrier, roofs, facades and floors, and satisfies the aim to test the exterior envelope. However, while the equipment to site level may be less than a whole building test, there is inherent complexity of pressurizing adjacent compartments and managing multiple fan assemblies throughout many locations and levels. This test has much higher risks of inaccuracy and would typically be more expensive due to the setup involved. Without due care, it can also still be impacted by risers, ducts, lifts, etc. between floors. Ultimately, the building is a whole system, and as such, a whole building test is the best way to measure the performance of the building envelope. The National Construction Code for 2019 included non-mandatory airtightness for the first time. Under this current code, verification methods for both residential Class 1 and 10A buildings and all other classes of buildings were introduced as optional pathways to achieving building ceiling requirements for the respective energy efficiency sections. As per clause V2623 as shown, the requirements for residential buildings was for an air permeability score of not more than 10. Though very achievable, the industry at large has sought to avoid the cost and risk and continued with the subjective DTS building ceiling provisions. Clause JB4, also shown, has been more widely adopted in the commercial industry contracts. However, it's common that the building classes targeted for the verification method are not applicable for the climate zone stipulated in the requirements. The application table shown identifies with green cells which classes of building in which climate zone can use the JB4 verification method. As an example, note that a Class 6 retail store or a Class 9 school, highlighted by the orange squares, does not qualify for a verification method in Climate Zone 5. As such, the building industry is still using the DTS requirements for building ceiling. What about NCC 2022 and beyond? The NCC 2022 public comment draft for energy efficiency and condensation management hints at preparations for airtight buildings in the future. This includes 1. Requirements for homes with an air change rate of 5 or less needing to have a continuous mechanical ventilation system. 2. Introduction of make-up air requirements to ensure the effectiveness of exhaust ventilation systems. And 3. References to AERA Design Application Manual 07 for moisture control in buildings, which requires an understanding of infiltration levels in design calculations to ensure airtight constructions manage moisture. We are now clearly in a transition phase to mandatory air tightness testing, mirroring the UK and US experience that followed their non-mandatory code introductions. Other signs of a pending air tightness future includes the introduction of Green Star homes with an air tightness credit, the Air Tightness Testing and Measurement Association lobbying for a permeability of 10 under DTS requirements for the 2025 residential code, Accurate Sustainability using the CSIRO Cheneth engine allowing star ratings to be modified by a change in infiltration rate. Studies show that the industry can adopt and manage the design and trade know-how for airtight buildings over time. A 3 to 5 year adaptation period is typical for residential builders, with a 5 to 7 year adoption period for commercial builders. The time to start the adoption of air tightness builds is clearly now. Founded by the Green Building Council Australia in 2003, Green Star is internationally recognised at the forefront of setting the industry standards for healthy, resilient and positive buildings and places. As of the 1st of August 2021, air tightness features as a credit element in both the Green Star Home Standard for one-off home designs and the Green Star Design and As-Built Standard for all other building types. 3 of the key submission guidelines for air tightness credits include using a suitably qualified practitioner, that is, testing must be carried out by an ATMA registered tester, providing an ATMA registered certificate of air permeability testing, and conducting air tightness testing as per Australian New Zealand standard ISO 9972. As part of the Green Star requirements, the air permeability performance testing targets must also be achieved in order for this credit element to be awarded. Under Green Star homes, an air permeability level of less than 5 for cooler climates and less than 7 for warmer climates must be achieved. Under Green Star Design and As-Built standards for commercial buildings, there are maximum permeability requirements of 15 for commercial residences and 20 for other commercial buildings to be met. As highlighted in yellow, similar normal levels of permeability targets apply for commercial class residential buildings, including apartments, hotels and the like, for 1 innovation point. As highlighted in green, low best practice air permeability levels can earn up to 2 innovation points. Requirements range from a very tight permeability of 0.2 for cold stores up to a very achievable 5 for hospitals. With regular assessment, we can build a picture of typical leakage issues and work with your building contractor to quantify how addressing these leaks could assist you with your future air tightness performance. We can also support your design team to plan for an airtight build. Based on your target permeability levels and via testing results, we can highlight regular issues that could be managed with changes to design. And finally, we can help ensure the success of your airtight building project by staging air tightness testing during the construction, including qualitative tests of unique features, lock-up stage air leakage diagnostics, and early post-construction reviews. The performance of the built envelope can be maximised. That concludes our presentation for today. We thank you for watching. We trust you are now comfortable with the basic air tightness concepts and are keen to take this knowledge with you into your next built environment project. Again, CPD questions will be made available via a survey. This will be sent to the email address you signed up with shortly. If you have any more questions, Suho is here to assist you. Please refer to the contact details shown here.